Test, test. 1, 2, 3.
Hello. Hello. 1, 2, 3. 1, 2, 3. याद है नाम? Yeah. Next.
Test, test.
One, two, three. 1, 2, 3. 1, 2, 3.
Right, I guess. So we are already live. We are recording. I guess we are ready, but we can wait like 1 more minute.
भूल जा रहे थे नहीं प्रोफेसर ने दिया मेरे हाँ
Move to front. Front seat. I want to see everyone in the camera. Front seats, please. Everyone. I'll make sure you are visible here. No, here and there. Not on here and there. Yeah, it's okay. Stay here, but the other is.
तो कहाँ था ओके
No. All right, guys. So welcome again to the third week in student presentation. This is advanced computer architecture, and we'll start with 2 more exciting talks, hopefully, on different flavor. So we'll try to sort these topics based on relevancy, but sometimes, like, we need to accommodate some of the urgency for students. So from time to time, you'll see some odd talks, but most of the time, you'll see all of them stacked around the same topic. Hopefully, I think by next week, you'll start seeing more diversity in the topics, and hope you'll enjoy it. Don't forget, we need your participation. Please ask a lot of difficult questions. We have strong candidate today, hopefully. So yeah, please feel free to ask tough questions. And don't forget, we need your opinion by the end of the talk to nominate the best talk for today, okay? All right, the floor is yours. Whenever you're ready, you can start.
Hello, good evening, everyone. Our paper is Smash co-designing software and hardware accelerator indexing for efficient sparse matrix operation. This paper was originally presented in Micron 2019 conference. We will start with the introductions. First, Nayeem will introduce himself.
Hi, I'm Nayeem Uddin. I'm a PhD student under GSU Computer Science. I have experience with GPU architecture. I'm here to advance bioinformatics.
Hello, everyone. My name is Nancy. I'm currently a master's student in the computer science department, and I'm interested in building agents, AI agents, and solving real-world problems with deep learning. Now, Ritesh.
Okay. So hi, my name is Ritesh Yadav. I am a master's student at Department of Computer Science. I have been working as a consultant and engineer for 5 years before coming to the master's program. I've worked in various fields like virtual systems and automation. Let's start with the presentation. Big no for chocolates and donuts. We have a healthy option, as our team may suggested. We have some fig bars. Next, there is a chance to win a Starbucks gift card if you participate well. So let's see who wins it. Yeah. Next. So let's start with the executive summary. So sparsity is very common in today's modern world infrastructure. It can be found in many modern applications such as recommender systems, machine learning, graph analytics. Because of the sparsity, we need some kind of compression method to store that. In traditional ways, it was stored using CSR and CSC formats, which reduces the storage, but it increases the pointer chasing or indexing overhead. And the core idea of this paper is to co-design software and hardware to solve this issue, where we use software for compression and we use hardware to solve the indexing problem. And then because of using this idea, the authors were able to achieve 38 to 44% faster results than the traditional systems on SPMV, SPMM, which are the metrics kernels which are used for matrix vector computation and matrix computation. Also, it only adds 0.76% of CPU over additional core area cost. So Smash can be a very efficient and a scalable approach to solve sparsity in modern world applications. Okay, so let's start. So this is a matrix. How many of you think this is a sparse matrix? Anyone? Do you think this is not a sparse matrix? Anyone? Why? Not many zeros. Same. So yes, it is not a sparse matrix. It is a dense matrix because it has diverse set of non-zero elements. Next, we have this matrix. Do you think this is a sparse matrix? Anyone? Why? No? Yeah. More than 50% values are zeros. Yeah, that's correct. This is a sparse matrix. Next. Do you guys think this is a Do you guys think this is a sparse matrix? No? Why? Lot of similar values. Yeah, that's true. This is also a sparse matrix. Sparse matrix always doesn't means that number of zeros accounts for the sparsity. We can go next. So we have seen that we have saw variation of a dense matrix, sparse matrix where zeros were prevalent. We saw another sparse matrix where 3 was prevalent. So we can understand that sparsity is not only about number of non-zero elements or zero elements in the matrix. It is also about the diversity of elements in the matrix. Yep. So now we will try to understand what is the role of sparse matrix in today's real world application. Sparse matrix are highly prevalent in today's real world applications. As the businesses grow and also the as businesses grow, sparsity in their data set increases. This is very natural as data collection becomes at scale. Sparsity becomes unavoidable in results in many of the massive data collection. Next. Now we will understand some of the applications where role of sparse matrix in today's world. First of them is graph analytics. So before starting it, we are going to do an exercise. Let's try to understand how many people do we know in this class. How many of you at least know one people in this class? How many of you know at least two people in this class? How many of you know at least 5 people in the class? How many of you know at least 10 people in the class? How many of you know at least 20 people in the class? So as I'm increasing the number of connections between ourselves, it becomes sparse. So this can be represented in graph analytics in such a way where we can point you as a node, and your connections are represented by the links to the other people. When we convert this into a matrix, we can see that we have users on the left hand side and the users on the top row, and ones represent the connection between you. So this kind of metrics or this type of graph analytics is used in social networking websites like Facebook and YouTube, where they try to find who are your friends, which are the channels you are subscribed to. So this helps in analyzing those. So as the number of user increases on that platform or number of channels increases, sparsity also increases. Next is recommender systems. So everyone knows here that many of the platform recommends us things here and there, from products to the content. Anyone wants to like highlight how those contents are recommended or how those products are recommended? Anyone? Based on? Okay. Anything else? Yeah, means yeah, so my question I would reframe like what is it based on? What are the recommendation based on? Based on our patterns, based on, yeah. So one of the example here is what we are going to talk about is Netflix. This is the Netflix price data set, where we have users on the left hand side and we have the content like web series, movies, and documentaries. And these points here define the ratings, or if the user has watched that or not. So every user doesn't actually watch every movie or rate every movie they see on Netflix. So it creates a sparsity in their data set. Next. So next application we are going to see is in AI. So we all know that AI is becoming more and more prevalent. And we all know one of the models used in AI is neural network. So to increase the efficiency of a neural network, or to increase the efficiency, or let's say the performance of the neural network, we mostly, what we do is we prune the neurons so that their weight are distributed, and we only get the details of the neurons which are really needed in solving that problem. And when we do that, we can see that a dense neural network is converted into a sparse neural network. Another way which highlights us in AI is when we do forward activation paths, as we could have learned, many of us in machine learning classes, where with every passing activation forward, with forward activation, the neuron weights tend to become 0. So that also creates a sparsity in the neural networks. And at the end, we are going to see an example of scientific computing. For scientific computing, there are different equations which use partial differential equations, like the Laplace equation, heat equation, the wave equation, where we try to point out the point from which the heat is producing, or from the point from which the wave has originated. When we try to do that, we try to only point out that area in the whole picture, and left all of the points in the data set at 0. So we ignore them, which creates a sparsity when we try to calculate partial differential equations in scientific computing. That were the real world application where sparsity is prominent, and we can see that sparsity can be seen in many of the applications which we use daily in our day-to-day life. To put numbers into perspective, Facebook has 99.997% of sparsity in their graph analytical system. Second, in YouTube, we have 97.69% of sparsity in their graph analytical system. At last, the Netflix price data set we discussed, it has 98.8% of sparsity in their data set. So this is one of the metrics, sparse metric collection, which is maintained by Florida State University and Texas State University. And you guys can scan this QR code to access this collection. So this collection is also being used by the authors to evaluate the SMASH. And it has many applications from material science, computer graphics, power networks. We have given examples of 3 of the data sets which are present in this matrix collection, and we can see the sparsity is less, the number of non-zero elements are less than 1% in this matrix. Next. Now Nancy will continue with the talk.
Okay, now that Ritesh has described the sparse matrices and how they're used in the real world, let's look at this toy example of a 10 by 10 matrix. So here, like, it's filled with 95% zeros. So if you see here, the data that is being stored is like we're storing 800 bytes of data. And next, the useful data in this is only the non-zero values, which is 40 bytes. These values that are zero, they represent that there is no link, or it's just the same information that is being conveyed. So it is not considered like a useful data. And then we have, so this is causing us a storage inefficiency because mostly it is filled with zeros. And the next thing is we are also going to have a computational inefficiency. Let's say if you want to multiply this matrix with another vector or another matrix, this is going to cause unnecessary computations with the zero elements because the zeros are not going to add on to our results. So locally storing this kind of matrix in the registers and caches is highly inefficient, and it's just going to be a massive waste of memory and computation. So what do you guys think that we need to do over here to avoid this problem of storing these many zeros and the whole matrix? Sorry? Sherry? Okay. Yeah, fine. Mm-hmm.
They have numbers, right? So you can use that particular number only, like only 5%.
Okay, yeah, that sounds correct. So let's go ahead. So what we can do is, let's say if you have a list of numbers on a paper and they are ranging from 0 to 10, most of them are zeros, and you have some values which are not zeros. So what would you do to remember those numbers? So what you could have done is you can just remember the non-zero values on that paper and just forget about the zeros. Obviously, you would need to remember the total count of numbers so that you know how many of them are zeros and how many of them are non-zeros, and just remember the non-zero values. And if I say, okay, we also need to remember the sequence of those non-zero elements, the way they are occurring, then in that case, what would you do? Yes, that's right. So you would be storing the position of that number along with the number itself. So that is what we have over here. This is a compression format, and this scheme is basically going to compress the sparse matrix using the row indices, the column indices of those non-zero elements. So I'm going to be creating like 3 arrays over here, row indices, column indices, and values. And let's say, for example, if we take the first non-zero element 2, so I'm going to store its in the row index over here in row values, and then I will be storing its column index and its respective value as well over here. So that way I am like only storing the position of those non-zero elements, and I'm working with only the non-zero element. Can anyone guess what would be the answer for the next element in this row? What would get stored? Yes, 0, because 0th row, column 3 and 6. That's correct. Okay. So like that, we would be completing for the rest of them. So this is the compressed row format, but this is the compressed coordinate format. But the problem over here is let's say if this one row has a lot of non-zero elements, I am repeating the same row index multiple times. And same way, if a column has multiple non-zero elements, I will be repeating that same column index multiple times. So I'm storing redundant data still. So another format has come up, which is being used a lot, which is the compressed sparse row format. So what we are doing is we are considering the same toy example, sparse matrix, and the column indices and the values are from the previous example. They are the same. But here, we are going to introduce something called as row offsets. So row offsets is going to be of size, number of rows in this matrix plus 1. So total, the length of this row offsets is going to be 5 over here like this. And this row offset is going to store the starting index of the elements in each row. So for example, 2 starts from column index 0, right? So I'm going to store the starting index for that row. Go ahead. This is how it gets stored. Now let's say for row 1. Now for row 1, where does this non-zero element start from, like in the column indices? So it starts from index 2, right? So we are going to store 2 here. So does anyone want to guess how would we do it for the non-zero elements in the second row? You need to store here the offset. That means the pointer to the column index from where the value starts. So it starts from index 3. So that is what we would store here. And next, yeah, so 3 would get stored here. And then next, how would we do it for row 4? That would be 4, yeah, because it starts from 4. And same way, the values also can be accessed because fourth index is also corresponding to 1 from here. Can you move ahead? So now that we have compressed our matrix using the compressed storage, compressed sparse row format, let's see if we want to multiply this with a dense vector. So SPMV, that is sparse matrix vector multiplication, this is kind of like a workload because it's used in the real world deep learning applications when you multiply like weights with the inputs that you get from a layer. So here, these are the row offsets, column indices, and values which we just calculated in the previous example. And now we have the input dense vector, which we are going to consider here of size 4 cross 1. Now we want to multiply this and store this value in the output vector. Ideally, what would have happened is we would have multiplied each row with the vector, dense vector, but it would result in like unnecessary zero multiplications, which we don't want. So what we would do instead is we would go row wise. Okay, so let's click next. So in row 1, over here, we are at row offset 0. Like here, we are going to find out what is the offset value. So that means row 0 values start from index 0 in the column indices. So I'm going to extract those values. I will also check the next value here to see where it ends. So I know it ends at index 2, so I will stop here basically. And that's how I get the column indices and the values that are there. Now, these column indices are going to be used to access the dense input vector. So 0 is going to access this, and 3 is going to use to access this one. So that means 2 gets multiplied with this, and 6 basically gets multiplied with this value in the dense vector. And then we get 2 times 1 plus 6 times 1 is 8 total in the output side. Like that we would do for the next row. So see, for the next row again, the offset value is 2. We start here, and then we access the corresponding index from here, and then we access the value, and then we do 3 times 1 is 3. Do you guys want to guess what would be for the next row? Yes, we would take this particular index and the value, and then you will get this answer. And then for the next one? Yes. So that is how basically we are doing the multiplication with this sparse compressed row format. But can you move to next? Yeah. So we saw the advantages of CSR that we are having. That is, it's helping us reduce the storage, and it is also like helping us avoid the unnecessary computations on the zero elements. But if you look at this title of the slide, I'm saying that this compression is slowing you down. So does anyone want to guess what could be the reason that even after doing all of this compression and avoiding the zeros, it's still slowing us down? Yes, that's correct. Like what kind of computation you're talking about? Mm-hmm. Yeah, but you're avoiding the zeros, right? Okay, that could be one possible answer. Does anyone else have any other answer? Parallel processing. Okay, that's also a good answer. Still less than our sparse matrix, right? Okay, like if you want to multiply with big numbers. Yes, yes. So all of these answers are quite plausible. But let's see what is actually happening. Imagine that you're working at a department store and you're given a list of products and also their prices. You're also given the location where that product is in the aisle. Okay, and you're tasked with finding the total price of these products. So as an employee, you would have to go to that respective aisle, count the quantity of those products and multiply it with the price to get the total price. Now, like since the list of products is there, the aisles are all scattered and you would need to go to different aisles to find the actual quantities. So this is what is happening over here. You're having this indirect data dependent memory access on X. We used row offset to find the column indices, and then we used column indices to find the respective multiplication in the X dense vector. So that is like an irregular access. So what will happen is mostly the hardware prefetchers are going to miss that multiplication because they wouldn't be able to predict the pattern in which we are retrieving the values or accessing the dense vectors. The cache locality would also be poor. And the TLB locality can be poor because we are again not able to predict the pattern in which we are doing the accesses. And next, you're going to pay frequent last level cache and DRAM latencies. So there will be multiple trips that you would need to make to the DRAM just because your caches do not have the value that you need. So there are a lot of cache misses. So what is happening is even when you're doing the execution of that simple multiplication, you're wasting time on getting the data. It's a memory bound process that is happening and the execution is less compared to the waiting on the data that we are doing here. So this is basically the indexing problem that is happening because of chasing these pointers and getting these non-zero elements. So as you can see here, the x-axis represents the different matrix operations that you can perform with sparse matrices like matrix vector, which we just saw, matrix vector multiplication. This is also sparse matrix multiplication. So in an ideal CSR scenario, here we are considering that this indexing overhead problem is not there. So imagine if this is not there, then you can see the drastic change in the speed up, like it's nearly 2.2 times that you're having the performance gain. Similarly, for SPMM, it's like double. Then again, the number of instructions that would get executed for an ideal CSR would be quite less compared to the CSR traditional technique that is being used. Now, this is because you do not have to issue extra instructions to get the data from the input vector X. So now to address this bottleneck, we are introducing SMASH, which my colleague Naeem would explain for this.
So until I pull up my mic, what is the problem? Indexing is the problem or the daylight is? I think I've been struggling with the daylight recently. So I speak to my kids back in India. It all became all of a sudden 1.5 hour gap instead of I think 2.5 hours. So yeah, let's look at how we can solve all of the indexing and of course the extra row pointers, the extra memory that we have required. Not just that, right? I mean, imagine even the number of bits that we were scaling, having to have all those pointers into local register form when we were processing inside CPU. So how we address all of them? So there is a new approach called Smash, and that what we introduce in there is, so we have a tightly packed software called a compression. Of course, we have revamped how we look at compression scheme, and then there is a new toy hardware sitting inside CPU that is responsible to read all these compression information and then process over things. And then one last thing is that to do all of that, we need new instruction set. So just a little computer architecture pill here, right? Always remember that whenever we have a hardware change, so we will have it via either the direct hardware or just the ISA, because that's how software world gets to know, and also the compiler gets to complete all of its own targets. Now coming to the software, so we know that row pointers, column indices, and non-zero vectors were problem always. So but we do look at from a hardware perspective. We'll get to that in a minute. But more than that, I think we have extra matrix parameters and the compression information that floats from hardware to software. Now in the new introduced tile, very small tile that we had called BMU, it has a very small local memory sitting inside, and then a logical unit that that helps you communicate from the CPU. And of course, there is interfaces lines from CPU to memory. New ISA instructions that we'll talk about, there are five of them. Each of them have individual functionality. Get to next. So let's look at software world, right? How software is looking at things. Next. So now, if you see here, we have 8x8 matrix. So let's look at how we do Smash software, right, into the software world. So first row, we get next. So we have a configuration here called 8:1. So meaning that this entire row will be converted from 8 bytes to 1 byte. Okay. Rather, it's just a bit in terms of when I have a bitmap, because I just need to token out here if it is 1 or 0. Meaning that if there is a non-zero element in my array or not is the question in the row. Now, if you look at it, we have one legate value here, 1. Can you go next? So there is again next row come in here. So there is one more 1, meaning that there is one non-zero value. So we'll automate it 1. There was a question actually. Okay. So wow, now that's fine.
0, 0.
So this tells you why timing is very important in a CPU world, right? If you don't match timing, you've actually lost a question. Also probably a Starbucks there. So okay, so timing is very critical in CPU world. All right. So next, this is 0 because we have no absolute non-zero element. Next again. Yeah. So they are all zeros. So there is now the question is there are 2 now. What will be the value here?
1.
Why? Why not 2?
Because the question is whether there is value or not.
Very
There
nice.
is value,
Excellent.
so 1.
So this bitmap contains only the information of a person exists or not. Right? That's all. Otherwise, there is no meaning. So yeah,
Starbucks.
good one. You want Starbucks? Starbucks still level up. So. Next, please. Yeah. So we again, continue to do bitmap like that. Now, this was first level of the bitmap. So we have second level. Imagine a 4K tile, because this is just a toy example. In the real world, right, you will have all these machine learning AI that you speak. When you go to GPUs, when you go to all those customer-centric product data sets, you will see that they are all bigger sizes in both tiles and also the overall problem. Okay, space. So now next talk about the bitmap 1. Can we now assume? So again, we evenly chunk these out. So let's start. Next. So this again, we have only 1. So now from here on, we mark only 1 because we have a legate value. Can you again look at the other one? Yeah. So next again is 0. So 0, 1 will also be again 1, and then 1, 1 likewise will be 1. So always remember that though we have the amount of compression being reduced, now there's no talk about indexing. There's no talk about we are fetching all that hierarchy of the row versus pointer indexes, and then of course the values. Nothing like that. We just have flattened everything up. Remember, this is how many bits do you need to represent each of its value here? Go back. How many bits do we need to represent each of the value?
1.
Only 1, because it can just be 0 or 1, right? So that is how it is. The beauty of that is just, so imagine a register which is 256 bits. That's it, done. So you have a bitmap done there. Yeah, next. Let's get to the hardware world. So hardware is again, we'll get to see what PMU first, and then see where it fits and how it communicates with the CPU, of course, alongside the software. So we have a general CPU versus memory. Now a BMU comes up here. So we talk about now hardware. So always remember, we had next. Yeah, always remember we had matrix information floating from software. There's a bitmap compression information we need in hardware, and of course the non-Z arrays that were sitting in the memory for having to have compute. Also the bitmap information, the registers that we were talking about, the hierarchy that we just created sits in this. Now row indexes and column indices are that information where we fetch back from the SRAM buffers as soon as we have the information being floated from the hardware logic when it kicks in. Go next, Ritesh. Yeah, have me. So how it goes is, first we scan all these buffers, all that they are bitmap information, compression information. These are parameters, say, what set of number of compression ratio, and then number of level of bit mapping and all that is being sitting here. Here we have matrix parameters, the original problem size. And then of course we read that, we scan, and then we read all these guys and update row indices and column indices to support CPU computation. Next. Now, yeah, hang up one next. So let's look at where BMU sits, right? One next. So we know that CPU is a general CPU have ALU unit, registers, control unit, and then of course level of caches, and then main memory. That's the native path. Where do you think Smash sits? This is pretty close to how Star works.
Again, can you repeat, please?
The BMU unit that we just look at, where do you think in the bigger scheme of things sits there in the hardware, in the real hardware? It sits in CU, it's in L1, in L2, LLC, or the main memory, the little component that we have seen. All the scary faces.
In between that,
I would have jumped out of that, okay? If somebody says Starbucks.
LLC. LLC.
Within LLC?
in
Pretty close.
between the LLC and main memory.
You are not eligible, by the way. Yeah, I think the exact answer. Excellent. And the reason is because, go next. How much? 1 second, oh, hang up. What information lies in L1, L2, LC, and the main memory? Again, a computing architecture question. Give me one card for Starbucks. Yeah. What information lies in caches versus the main memory? What information, what set of information lies in caches versus in main memory? Don't look at question, look at this.
That's why I asked.
Excellent, almost there. What terminology generally we use in computer architecture to represent that? Go next. This is very important, all right? This could just be your advanced architecture interview question also. So there is always, remember that there is always a temporal versus spatial data floating in entire machine, and that caches are always close to, I think we can give it that. And that caches always have temporal data, which means we keep reusable data inside cache, but that pretty close to the last level caches versus the main memory will have information which is not so natively, but remember that they are consecutive data sitting there, so it's a connected data sitting there. That's why now that we have already computed addressing and all scheme in in the software world itself, so we don't need to we don't need BMU to sit near to CU compute, right? CPU. That's why we keep this here. Okay, next. Yeah, I think we have it. Good. Next. Was that for me or her? This is very scary. Okay, so I want to make sure I'm giving these drills out every time. So okay, so running in Smash on running SPMB on the Smash. So we'll do it quickly. So we know that this is our matrix and then the vector computation. So we have these compression techniques. We've just compression ratios. We have just now brought up. the number of instructions that we know that, you know, there is that information to instruction to fetch bitmap. There is an instruction to fetch matrix param. There is an instruction to fetch SRAM buffer. It inherently tells us, right, in hardware there is no magic, right? So to do anything and everything, there is a sequence of step, there is a sequence of principle, there is a sequence of foundation, all the way from software to compiler to hardware. All right. So that's why you continue, go down. Next. That's why we have this mat info fetching the matrix sizes, and then the bmap info fetching the bitmap parameters. The read bmap fetches the SRAM buffers, and then of course, yeah. So now to compute matrix vector multiplication. Next. We can go around. All we need is, you know, as soon as we have that information sitting with us in the CPU, so we need those read indices and column indices to be able to fetch non-zero arrays, and then we compute the matrix vector multiplication. Go next. So that is all. We got 9 versus 4, 36, 1 versus 2 positional. Again, look at that. But just make sure that, so whatever I went to the matrix multiplication is just the flat NZ array here, not this matrix. Remember that. Okay, that's how we saved all that computation. Next. Yeah. So the entire experiment was set on ZSIM simulator. Now to introduce simulator, right? In any typical simulator, the same all similar. It's just that this has extra libraries ahead of the user space. This is all your host machine, which is what's sitting in your laptop always. Now, but for the simulated machine, we have this pin library, which is from Intel. It has a lot of hardware related register information in the software world, which maps to, you know, to your software can act as a hardware actually. And then they have some flavor software to be able to behave that, to make it behave as a cache, CPU, registers, etc. And then they have written on top of that as a smash, which has this part of the code had only the bitmap hierarchy, BMU, and the ISA. Let's see.
Okay, thank you, Naeem, for explaining about Smash and its working. I hope everybody's brain caches are full and they are going to like store all of this information after the talk in your SSDs instead of like forgetting about it. Next, we are going to talk about the experiments and the evaluated data sets that they have used in the experiments. They are using 15 diverse set of sparse matrices from the suite sparse collection, which we have seen before, and they are from like Florida State University and Texas University. So it's this is the data that they have used. M1 through M15 are the different matrices that they have used. And this is the sparsity, which is in ascending order. And over here, this represents that the matrix is more sparse. And here we are like going towards lesser sparse. So this is more dense compared to this. And then we have these 4 input graphs, and we are using 2 workloads. Now these workloads are similar to like SPMV and SPMM, which is like matrix vector and matrix multiplication. But for graphs, we need to use something like PageRank and betweenness centrality as the workloads to evaluate. So coming to the results that we get with Smash, let's see that. The first one is the performance improvement that we get for sparse matrix vector multiplication. The x-axis represents the matrices from M1 through M15 and also like the average case across all. And as you can see, no matter what is the sparsity of the matrix, we are always getting this upward trend. And that is because we are able to avoid the indexing overhead that we get with this baseline CSR. And on the average case, you can see you're getting like 38% faster than the CSR format. Next, coming to the number of executed instructions for SPMB, again compared to the baseline CSR, which is over here at 1, the normalized number of instructions executed for Smash on an average is quite less. It's 47% less, which is in this dark blue, which represents Smash. Next, coming to the performance improvement for SPMM case, what happens here is, here we are going to be performing the indexing operations twice. So compared to the baseline CSR, the performance improvement is even more. Now that is because the double the number of operations are being performed and we get an overall 44% of improvement compared to like the smash that we had with SPMV. And this represents the more sparse matrix, and this is the less sparse. So as you can see, this upward trend that is happening. So as the matrix becomes little denser, we are able to use smash to even perform the computation faster. And that's because the non-zero arrays would be having less number of zeros and more non-zero values to work with. Now next, coming to the number of executed instruction for SPMV, again, on the average side, you can see it's 45% less compared to the baseline CSR. Next, please. Now, talking about the graph inputs, we have G1, G2, G3, G4, and the average across all of them. And this is the first workload, which is page rank. And the next one is the betweenness centrality. So as you can see, the performance gains are 27% and 31% respectively, and they are less compared to like what we get with matrices instead of graphs. Now, this is because when you want to do the page rank computation, the work that Smash does for us is quite less compared to the actual algorithm that runs behind page rank and betweenness centrality. So the values are little less compared to the previous performance gains. Now, next please. Yeah, now Naeem will talk about the related work.
Ritesh is still in pipeline. One more computer architecture fill. Okay. Now, so coming back to the related work, let's see what people have done in this area to improvise all those solutions beforehand. So first principle first, right? Always matrix multiplication have been analogy of having to have row versus column. So A have been always logged on to row, and B matrix have been always logged on to column, right? So these this group especially have flipped that up because they have looked up too few data sets, and that they felt if they get to the first matrix as the column and then do a second matrix as a row, then they were saving a lot of compression ratio information. They had extra hardware in the processing elements that really assist in having to have a lot of sparse computation. This is basically a SIMD style hardware. So hence, they had that chance to do because when they flip that from the tiling perspective, how the data is being read in the system itself have benefited a lot. But the contrary on the challenge is that it required 4% or rather 2% on the Atom versus Intel Xeon processor. These are data center processors, which are very big in sizes. So 4% area there, no IP or SOC manager will give you that much area on the floor planning. Next, of course, this was again done in the simulator world. So when it gets to the real world, it might have a little friction over there. The other issue with this was the data sets were only SVM related. So not many type of sparse metrics were evaluated. Next. So the other work was around graph analytics, because this is one big area for us as a consumer to accelerate sparse matrix multiplication, or rather vector multiplication. As we know that each node in the graph is unique in its own functionality, and hence to compute on those things, what we have is we have always learned that there is no cache. The cache is not generally helping. So now what they've decided is to have a smart scheduler sitting just beside the cache to make sure they pipeline it really well accordingly whenever they are in the set of tree of the graph they are in of the branches. When they did that, I think they have had better data related to nodes being available just before they get to processing, and hence the prefetching was really good in that sense, and it was able to have efficient scheduling, and then that thereby increased performance of the design. Now there is one last work on the parallel sparse matrix multiplication. This was, I think, one of our friend was just talking about parallelizing the CSR itself. I think he was way ahead in time, but you cannot do that in computer architecture. Remember that everything is timing, so you cannot think of the future because the data comes in pipe, and also the instruction sequence floats in that order. So you have to hang up until you share your thoughts. It's very simple. Again, we have that values column indices and the value vectors, row and the offsets. It's just that the difference is no go up. It's just that the difference, if you look at it, the fine difference, right? Just go up once. They have split these two processes, multiple processes. So now that we can parallelize each of them. So P represents a process here. each of them can be a different process. And then thereby they were paralyzing all the entire effort. The only thing was, because remember that we have to, since this is matrix multiplication, you have to accumulate over things in your row versus column form. So do that next. So here, that is how, they keep um, doing entire processing of the one of the row, and then they accumulate thereby, and then continue to accumulate of over those partial sums. The only challenge with this was having to have this was having the merge path based load balancing framework only for the CSR again. So there was nothing like smash as in perfect, because everything had its own taste of flavor and was very centric to given problem. But smash is very generalized in nature. It doesn't really care about what sort of problem set it is, and it addresses too many smash types in the real world.
Hello, hi everyone. So now we are going to break down Naeem's and Nancy's thought process in strengths and weaknesses, how Smash performs, what are the strengths, what are the weaknesses. So in strength, hardware co-design and software co-design works good here. It is one of the advanced strengths where we are able to solve the problem using both software and hardware. It has a major performance gains, as Nancy told us in the result section. We were able to see that 38 to 44% of performance gains were seen. On CPU area, it just adds a modest 0.076% of area overhead. Works with any kind of sparsity pattern and kernel. Now for weaknesses, as Naeem told us, there are 5 new instructions which are needed to make BMU work with the CPU. So those instructions may not be available in every kind of architecture. So it is a weakness there. Software has to do a lot of upfront work because the compression, the bitmap hierarchy happens on the software end. And today, in today's world also, CSR is more prevalent than bitmap hierarchy. So we will have to convert CSR to bitmap hierarchy. It also adds software upfront. Next, we have design was verified on simulator. So we don't know if it will perform as well on real hardware or not. Compression ratio can be a trade-off, as we saw that despite of the compression ratios we had in a bitmap hierarchy, we were still storing zeros. We were not, it was not like we were only storing non-zero elements in the our memory. We were also storing 0 elements because of the compression ratio set there. Next, for the critiques, we have evaluated 4 papers which came after Smash. So we have included the QR codes. You can scan them and look for those papers. One of the paper is Mentor, which was published in 2024, which talks about bitmap metadata dominates memory traffic. So it tells us that bitmap hierarchy can increase the memory traffic with more than 66%. The next paper was published in 2025, Electra, which talks about bitmap compressed matrix inflectuate compute needs extra logic for pruning, which also criticizes the bitmap hierarchy of the paper. The 4th paper was Express in 2020, which tells us about metadata processing overhead outweighs the compression benefits when sparsity goes beyond 70%. And the 4th one is the SPMV survey, which tells us that we are ignoring the pre-processing converging of CSR to bitmap hierarchy. We are ignoring those performance, and they can result in overestimating the runtime benefits which are talked in Smash. Next, let's understand what are the future direction, as this paper was published in 2019 and now we are in 2025. So having a dedicated hardware like BMU is not so much feasible nowadays, and we can use PIM processing in memory as taught by Professor, which can be used for BMU processing. Then we can use SPMV and SPMM acceleration using sparse transformers. We can instead of using custom ISAs, we can use RISC V vectors and prediction extensions. And for cache side bit scanning, we can use HBMM stacked processing in memory or 3D RAMs. And co-designing software format, we can use tensor formats, which are more blocked and structured rather than bitmap hierarchy. Next, these are the two papers we have, which we found that were the best in the publication related to the topic. One is from which is called Sigma. Both are from Georgia Tech, and you can scan the QR code to look up both the papers. They both talk about how we can leverage bitmap hierarchy, and we can use them to interconnect DNN testing, and how spare matrix computation can be increased using tensor formats, which we talked about in the critiques. Next. So for the takeaways, we tried to do the implementation for Smash. So we were successful to implement the ZSIM in our laptops. We set up in Ubuntu on i5 processor with 24 GB of RAM. It was installed on Ubuntu. We faced challenges in setting PIN, which is one of the prerequisites for ZSIM. There were a lot of dependencies issues with PIN. As ZSIM support has ended 2 years back, so there is no support available for ZSIM right now, through which we can, and there is no update also ZSIM for modern softwares or architectures. We wrote a custom CSR, and we were able to compute those CSR. We were also able to compare it with regular matrix multiplication if we don't use compression. If we there are two screenshots here, one of there where the density of the matrix was 0.01, and the other was when we had a density of 0.01. At the end, we can see that the speed up for 0.01 was 164.5x, and for as density increases, the speed up actually it is not in the screenshot, but it was around 16x. So we can understand that as Nancy also explained, as the sparsity the density increases, the computation used, or the computation speed up also decreases. Yeah. Next. Thank you. This is the QR code you can scan and read about our paper. Do you any questions? So generally talking, there is a more up performance seen in SPMM and SPMV rather than graphs. In graphs, the performance gain was not as significant as it was seen in SPMM and SPMV using Smash. Anyone else? Yeah. Oh yes. Sorry.
Hi, nice presentation. I wanted to ask, like, there's a very classical compression technique of Hoffman encoding that we all know of, information theory. So I was wondering, like, is there some kind of comparison with that compression scheme, because the main challenge here itself is the memory footprint of like sparse matrices and how to do computation. So how do you think like that would be applicable like for this particular problem, and like can there be a comparison between the two?
I don't think that the direct application on the Huffman encoding, because the problem set here is not to map between two or two of kind, right? It is to compress like bigger scheme of things. There huge number of so the problem is not like a compression on having to just attack a memory problem, because we have to even fasten up compute also. So looking at both the ways of the world, I think then that really doesn't fit into this, and hence the CSR was predominantly the better choice to do sparse. And everywhere we look at that is mostly the dominant compression used even for today also. because of the fact that there are lot many standard frameworks, including all of our TensorFlow, be it AI, any field, HPC. I think they have all had CSR as a predominant compression technique, and hence then now when we look at the baseline itself, the CSR makes sense because we have that action being done already on the all the M0 to M15 that we have spoken about, and this problem is very niche in terms of having to accelerate just the sparsity, but again it has too many implications on too many fields. I think the major goal was to accelerate all these the sparse matrices that we were looking at first as a first order, and then of course they had to really back it up with doing graph analytics and all, which they have not found well outcome from.
Yeah, thank you. One more question. I was also wondering, like, since you like showed the case of like a very simple try example for integers, like they're comparatively easier and simpler to store. So like, how do they handle like floating point numbers or like the precision values?
So like in the compression technique, it is not only about integers. We took integers just to simplify it, but the handling on the memory level doesn't changes. We are only doing compression. We only don't want those redundant memory to be saved. So there is no change in handling how we are handling integer or how we are handling float variables here. It is not about that. It is only about how we are able to reduce the memory storage there, and we only remove the redundant, and how we are fastly able to capture the indexing of those elements then, and do the computation as fast as possible. So there is no change between integers or float handling of data.
Okay.
Yeah.
It's just about like working with the memory addresses, like how fast you're able to do the indexing and find the value that you require to do the computation. So the value that you get does not matter because that you're going to use anyways, but how you index it is important. And that is what we are addressing here with the software hardware co-design.
I think as far as I understand, I think the data sets were lossless that they were evaluated. Yeah, we can definitely. It really depends on how I think it comes to the dynamics of the compression itself, because now you have got one more identification to be taken care of in terms of lossy, right? Because you have to store that information, correct? So I am not sure at this point. I don't think these guys have at least covered that the lossy one. But then I think what we understand is at this point, my understanding is that it is definitely a lossless.
Yeah. One more. Do they discuss the theoretical bounds on the time complexity of the algorithm, or is it like a practical data science only?
I think that is very excellent point, and the reason is that now there is a catch here. When the size of the matrix increases, the bitmaps hierarchy increases. Remember that, right? We just had only 8 times 8, and then we already had 2 levels of it. Now imagine a 4K, 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 right? So then now why it's a challenge is you have hardware limitation on storing that bitmap information itself in terms of 3 registers, right? So as long as you go up in the time, so you have got that address, you've got to address that multiple iterations of the bitmap loading itself to the memory. And at that point of time, the now CPU needs to do that in batches, right? Because of course it is in batch now. If the size of the matrix is huge, I think one of the concern was having to address the bitmap set.
One more thing was like in the paper they have talked about the compression ratio. If the compression ratio is not selected at the best, which suits the pattern of sparsity, it will increase the overhead. So the time complexity increases there. So if the compression ratio is selected rightly and which can identify the sparsity more prominently, then the time complexity decreases there.
That's a user-defined parameter, the compression ratio, right?
Yeah.
Thank you.
I think all the workloads have that optimal decision there.
Yeah. Anyone else? We have a question if you guys don't. What is compression? Anyone? Yeah. Yeah.
Nancy, those questions were very good.
Anyone, what is compression? No?
Thank you.
Yeah. Yeah, as said, she's right. One more question we have is what is indexing overhead? I think Nancy explained it. Yeah. What is indexing overhead? Anyone? The compression? No. 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 Yeah, that's correct. Yeah. Yeah, point it is. Yeah, he's right. Next, how does the reframing of indexing as the bottleneck changes how we should evaluate existing format like CSR? Are we overvaluing storage efficiency at the cost of computation? The question is long, but it is a yes or no.
You say yes, we say no.
Yes. Why? Anyone? Why?
Just that they're asking whether using CSR, are we only concentrating on the storage efficiency or on the computation side as well? Are we trying to?
Yeah. Yeah, that's right. Also, one more point to add, in bitmap hierarchy, we are focusing more on efficiency of computing. We are not focusing on efficiency of storage. We are storing 0 elements in the memory.
CSR was better in that.
Yeah, CSR is better in efficiency of storage. Next, what impact of performance can be seen using only the bitmap hierarchy compression technique without the hardware BMU compared to CSR? If we remove the BMU from the picture and we only use the bitmap hierarchy, do you think it will increase the performance or decrease the performance? Anyone? Do you think because of the hardware, we are getting more efficient results? No?
Yes.
Yes? And if we compare it with CSR, do you think it will still perform better or no? Probably better. Yeah, we have not discussed this in the presentation, but it is one aspect of the paper where they talk only about software only approach, where they have removed the BMU unit and they were still able to achieve 5 to 10% increase in SPMM and SPMV results only using bitmap hierarchy. Thank you. And
All right, guys. So for those who needs test. So it's one, and please try avoid clicking. No, don't.
Just
You click it. Put it or keep holding.
Hello, everyone. This is Shreya, and she's my teammate Shreya. And today we are here with an interesting topic, CoNDA, efficient cache coherence for near data accelerators. Here you can see a picture like normal traditional coherence and also coherence with like using CoNDA. So actually here, this is a kitchen scenario. You can see two chefs. One is CPU, another is NDA. Like they work as two processors. And also there is a head chef guiding them with the instructions. And in the traditional coherence, it's like the CPU and NDA keeps asking for the instructions every single time when they wanted to use whatever ingredient they want in preparing a dish. Whereas in CoNDA, it saves time, like not asking every single time. So they assumes like all ingredients are available readily. They don't even frequently ask for the head chef what to use and what not to use. So after completion of the dish, they go to the head chef and the head chef will tastes the dish, and if there is any conflict, then it redos the final validation step, which is the CoNDA. And yeah, this is a key idea. Imagine like, as I said before, is a kitchen scenario. Like chef one is the main processor, CPU and NDA. Like both the chefs are working on different dishes. Like they use some common ingredients, for example, flour and sugar. So yeah, CoNDA enables like efficient CPU NDA coherency, like which enables like run optimistically and also valid cache permissions. Wait. So here, this is a smarter way which helps NDA. Yeah. So which helps CPU and NDA share data efficiently without wasting time and energy with constant communication. So instead of checking permission every single time, the data is accessed like at the end of the session. So here it reduces off-chip coherence messages, like not frequently asking, and also it preserves shared memory. Like even though CoNDA changes how coherence is handled internally, so programmers still see there is a united memory which is shared, and it also handles conflict only when only when they actually occur. So yeah, after at the final presentation, when the presentation is completed, you can understand what is the problem, impact, insight, and also the solution. As I said what is the problem? There is a traditional cache coherence problem, like messy. Messy is nothing but it's a traditional coherence problem, modified, inclusive, shared, and invalid. It actually modified is nothing but it updates the data, and shared is like both the CPU and NDA will have the shared copy, and exclusive is like both will not have the same copy, and only one will have the same copy. In invalid, both must update, like one will be having a different copy. So yeah, solution for this is CoNDA introduces a new, smarter, optimistic problem. Like it validates if any conflict happen. If everything is fine, it keeps the results. If there is a conflict, it just redos the task. Inspiration for this paper is like CoNDA is inspired by optimistic concurrency control, which is used in databases. In OCC, multiple users can work on a same data at once, and systems only for conflicts after they finish, not after every step. Next slide. So this is a problem statement, like traditional cache coherence mechanisms, like they use a large amount of unnecessary off-chip coherence traffic messages, and there is a wastage of time and energy and also less performance. So this makes it difficult for the NDA to use their benefits. So here is a background NDA and coherence things. We have three concepts here: NDA, near data accelerators, cache coherence, and also fine-grained coherence. In NDA, it's a small compute units inside a memory, like mainly HMC and HBM. So NDA are tiny processors placed right next to the right next to the memory or inside a memory. Because they live beside the data, they don't even have to ship it into the CPU to do work. Example: think of a mini chef inside inside the pantry who is chopping veggies right next to the kitchen, so that NDAs will be helpful for the CPU to access the data very quick in a quicker manner. And also handles the data intensive tasks using like graphs, databases, and analytics. For example, we can use this near data accelerators in a kitchen scenario, and also in also the network, like Facebook networking examples in real-time problems. And coming to the cache coherence, here the memory keeps view consistent across the CPU and also the NDA. The CPU and NDA each keeps local copies, which are caches, individual caches. Like coherence make sure everyone sees the latest values, which is updated. And for example, if CPU and NDA both are cached, and if example x is equals to 10 and 10 and NDA's value is 15, so coherence tells that CPU both will have an updated value, not the old value. Traditional protocols like MESI don't scale well of chip messages, like they work on CPU cores in the same chip. So with NDA near memory, coherence messages must travel off chip, which is a bit expensive. And coming to the fine-grained coherence, here it tracks all the every tiny message, which is of 64-bit, and it's very precise. So yeah, it enables fine sharing between the CPU and also the NDA, and it causes heavy off-chip traffic messages. So if precision is like loss of messages. Next slide. So here is a question for you, and if NDAs are built inside memory, why do we still face cache coherence problems with the CPU? Sorry. Yeah. Yeah. So we'll discuss about the application sharing analysis. And I have a question. Do CPUs and NDAs actually share data? Anybody? Okay. Yeah. But actually the question is like CPU and NDA actually share data?
No. No.
The answer is yes. Sorry, there is no donut. So
Actually, the previous question was the same question that was asked again.
yeah.
The question previous was the same what they asked.
So here are the workload examples. First comes the graphic analytics. Like we are taking an example of Facebook, like a social networking site. So in the storage, like the data is stored in a graph format, where CPU handles like multiple updates. Like when a user adds a new friend, the NDA might analyze the same graph to suggest people in the Facebook when they click follow or in the same way. So both are using the same data, like friend connections. So they almost share the same memory. So next, the HTTP databases. HTTP are like, somebody can tell me the full form of HTTP?
Can give you a clue. It is picks up two different types of databases, two different types of queries or transactions that they are doing.
She almost said the answer. Okay,
Think of a database and try to answer. What you do in a database? What exactly?
almost
But
half
not-
correct.
It's hybrid transaction analytical.
Okay. You can get full donut. So this happens in a system like shopping websites and banking apps. So the CPU handles live transactions, like adding orders, updating balances. Then the NDA runs analysis, giving the total sales data and also spending trends. So here comes the key observations. And first is like high data sharing between the CPU and also NDA. They often actually share same data like user lists and product tables. For example, like CPU updates a product stock and NDA reads the same stock to calculate the total. And second, it's very few conflicting rights. Like if suppose she's cooking pasta and I'm baking pizza. So she'll use some different ingredients and I'll be using some different ingredients. There is less chance of having a conflict. So that is what they mean. So next, only 5 to 7% of CPU access collide with NDA lines. Like out of all the data, only CPU works on a tiny part which overlaps with all the NDA users. So like example, only 100 things of the CPU, only 5 to 7 will collide, which is a rare scenario. Less than 1% will have a right and right collisions. Okay, coming. Now let us know why this existing solution is failed. Okay. The figures explain about old methods used keeping like data consistent between the CPU and NDA, and any of the process did not work. And we have three processes used like non-cacheable, coarse grained, and also fine grained. All of them fail to balance the performances. And somebody can tell me what is non-cacheable meaning? What is the meaning of non-cacheable? Sorry? Not exactly the same. Yeah, yeah. Okay. So the NDA does not share data with the CPU cache at all. So it goes directly memory with to every read and every write. So coarse grained is nothing but the system divides into large chunks like regions. So if one small part of a chunk if it's changed, then also it throws away the whole chunk. Fine grain is one which tracks the tiny chunk of the data. Where something changes, it sends a small update in the message. So if we see figure 2, it shows how memory system energy is with all the NC and CG and FG, how it happened and what are the analysis of that. It shows like non-cacheable are the highest, and they use the most energy because CPU keeps reloading data from the memory. And here coarse grain bars like are bit low compared to the NC, and they are like flushing like large chunks, so that is why they are low. Coming to the fine grain bars are bit higher than the CG, so that we can understand there is a low energy, so that there is a waste of syncing of the memory. Coming to the bottom graph, you can have a look. We have high. So this is a speed of graph, and we have high value for the ideal NDA. Compared to CPU, for only CPU, it is low. And in simple words, even though NDA is supposed to make the system faster, the old methods stop it from pulling up the speed, reaching the speed. Here there is a table, you can see approach, idea, and limitation. For non-cacheable, the NDA bypasses the coherence, and the only limitation for that is CPU cache misses will increases. And coarse grained, the idea is flush big regions, and the limitation is too conservative and many flushes. And for fine grained, messy is per line, and too much of off-chip messages are going on. So here is a CoNDA key idea. So by previous slides, you might got an idea how CoNDA is working. So it's nothing but it runs first and it checks later. The process is like NDA executes optimistically, and it records the read and write sets. On every commit, like it validates when CPU writes, and if there is a conflict only, it gets re-executed. You can see the flowchart like execution optimistically. If it validates, if it's yes, it will roll back. If there is a conflict, it rollbacks. If there is no conflict, and the task will get executed. Next comes the execution model. We have three phases in this. One is optimistic execution. So what do you mean optimistic execution is? Anybody can guess? Yeah. So the NDA starts immediately, assuming that there is all the permissions are valid, which is a powerful funda of CoNDA. So as it runs, it records all the memory addresses to read and write, but not as long as it's listed. So it stored them with the signatures. So next comes the commit phase. The NDA will pause the execution. It sends to the NDA. First, the read set to the CPU, and next to the directory. Then it sends the directory to CPU. Next. And next comes the conflict handling. So here, CPU, if CoNDA re-executes the NDA segment, now the fresh CPU will update. So if there is no overlap, the NDA results will be committed and move on. So again, there is a question. So what happens if a conflict is detected during the CoNDA execution model? Yeah. So here is an execution timeline of NDA. This will tell like basically CPU how CPU and NDA work parallelly. So there are both CPU and NDA are working parallelly. So there are several operations happening here. C1 to C4 are read and write operations, which this CPU is performing, and N1 to N3 are the operations happening because of NDA. And this means like both are using some of the same data with the variables X, Y, Z. This is like two chefs, CPU and NDA, cooking the same dish using the same kitchen with the ingredients. And checking with the conflicts is the step 2. So checking with the conflicts after NDA finishes, its first chunk of the word is N1 to N3. First the CoNDA checks. So did the NDA read something that the CPU changed? Yeah. NDA reads said like what with what is nothing but what NDA reads. So if they overlap, it means like CPU is modifying something with the NDA used, which is called a coherence violation. And in the figure, CoNDA finds both touched X and Z. So there is a conflict. The system flushes or like an NDA works for both parts of the re-execution. So it performs later. And there's a second phase. Sorry, there is a third step, which is continue execution. After fixing the conflict, the CPU and NDA continues. Now it continues with the C5 and C6. Successfully it will execute, and the NDA from N4 to N6 also again executes optimistically. So in the second conflict check, there is no overlap found. So they did not touch the same data in conflicting ways. So the NDA's results are safe and committed. So you can see them in a diagram given there. So last is effective effective over ordering. So on the right side, you can see a column. So there, the CPU writes and reads and keeps the order of all the CPU and NDAs. So after this, the conflicts are fixed and the NDA's segments are changed from N4 to N6. So the CPU continues later operations successfully. So this maintains the correct memory order throughout the process. This is a timeline of NDA. And this is the CoNDA architecture. So here are the 4 main steps of CoNDA architecture. First is offload and optimistic execution. Here the CPU sends the offload and workload messages called NDA kernel to the NDA, and the NDA starts running immediately into the optimistic mode, meaning it assumes it has already given permission, all the permissions like reading and writing permissions. So while running, the NDA records all the memory addresses, it reads and write assignments. Second step is concurrent execution. Sorry. While the NDA is working, it is to an assigned task. So the CPU starts running from the parallel instructions which is going on. Both are active at the same time, so that they are said to be executed concurrently. This parallelism will give CoNDA its a speed advantage for both the CPU and NDA. Third step is signature exchange. Once the NDA finishes all the concurrent tasks, so it pauses and sends its signatures back to the CPU, and the CPU compares the NDA signatures with its own memory activity to check whether where the memory is accessed with the data in conflicting ways. So why do you think it is important? Signature is like a small data with a small size memory. So no, it's an original source. So coming to the next, okay. Last comes the coherence resolution. So if there is like CPU and NDA did not touch the same data, so everything is fine. The NDA works with the committed kept data, and if there is a conflict, both the used and the changed data will be executed, and the NDA must re-execute just like with the small parts of the latest updated data. And the result of this is like both CPU and NDA stay consistent and the data is consistent. With the final data, we can avoid unnecessary communication and unnecessary requests to the main memory. The Shreya will come.
So as you've seen the CoNDA architecture till now we will just, yeah, okay.
Inside the CoNDA experiment, okay.
No, it's not a question. So once you've just seen the CoNDA architecture, now you just adjust how did they simulated the CoNDA and evaluated the CoNDA in a real-time environment. They did not use a real computer, but they just used a simulator Gem5 for programming the total CoNDA efficiently. So what is a Gem5 simulator? It is actually a virtual CPU. It actually acts as a virtual environment and it actually works even as a real computer. It has a CPU or access memories or caches. It simply acts same like as a computer, real computer, and they have checked this. They have used this system for evaluating the CoNDA. So coming to the memory, they have used this hybrid memory cube, which is a 3D stacked memory, where the memory is placed in a vertical manner, so that whenever the data is accessed by the NDAs, which are placed near to the memory, the CPUs, the data can be accessed very easily and very fast. So this 3D stacked hybrid memory helped in accessing that memory more faster in the CoNDA. Then next comes the second step is the cache coherence model. What exactly is the cache coherence is? So as Shreya was mentioning regarding the two chefs example. So if the two chefs were creating a same dish, and if the first chef added a salt to the dish and the second chef is not known about the dish, that the first chef has added the salt, it is the outdated memory that the second chef was having from the chef one. So that outdated information that was given for the chef two is the cache coherence which is the nonsense that is being present between the chef one and chef two. This is the same the cache coherence modeling. They have used a Ruby which keeps the sync of both the NDAs and the CPUs in a sync while sharing their data. So they have added two different directories in the simulator. First is the NDA directory, which stores all the data that is shared by the NDA. And the second is the main CPU directory, which stores the data along with the data that is shared by the NDA and all other data that is present in the system. Yeah, in this protocol, in this simulator also they use the Macy protocol to keep the caches consistent. We already discussed what exactly the Macy is, which is the modified, exclusive, shared, and inclusive invalid protocol. Then coming to the system configuration. So this is how the system configurations are there. First comes the processor. Yeah, the first processor, which has 16 core, which has 8 instructions per cycle, and it is run on a 2 gigahertz frequency, which is out of order. What exactly is an out of order is rearranging the instructions as to make the performance of the system more faster. And it has one private 64 KB cache and a 4 MB shared cache, which is 8-way, and the coherence mechanism that was used was Macy. For the processor, this is for the processor. Then next comes a near data accelerator. For the near data accelerators, they had 16 NDAs per stack, which is a 1 instruction per cycle. They use the same as in the processor as 2 gigahertz frequency. And they had one cache, same as in processor as a 64 KB private cache. and they have used the same coherence mechanism, the Macy. As we already discussed, the memory that was there was hybrid memory cube, which is 4 GB cube, which has 6 vaults per cube, and each vault has 16 banks. Coming to the memory that is they have stored is the DDR3 1600 and FRFCS scheduler, which is the FRFCS scheduler is something that whenever whenever the memory that is accessed, the fastest memory that is available, that is being given to the system. Then next comes the coherence checking over it. First the checking. So now we have developed the total system. Now we have just checked how the coherence is being checked between this on the system. So for sending signatures, they have used this 20 cycles per each for every task that is being processed. For 20 cycles per each one signature is being sent. For the comparing signature, for every 2 cycles, they have compared the signatures and checked if there is any invalid commit is being committed. Then for the invalidating cache lines, in the cache, while the cache is being shared, if there is any invalidating cache, then the 8 cycles per line is being checked. For the merging data, they have used the 12 cycles per line. For the rollback or the rerun, when there's a conflict that is occurring during the commit phase, then they have used 8 cycles. For the total simulator that they have, for the CoNDA that they have built, they have only used 8 cycles for conflicts that are being raised. Because the NDAs, the CoNDA is will have lower conflict rate, so it will only have a few conflicts that are being occurred. So now we talked about the speed of the system. Now we will just look at the energy modeling. So they have modeled DRAMs, caches, and interconnects. Interconnects are something that they have connected these DRAMs, caches with each other. They have used the CACT P6.5 for the cache energy. And they have used the prior energy per bit model. This is the efficient thing that every researcher has been used for their research works. And the communication there was 3 picojoules per bit for memory links. So now we have seen the energy and the speed. Now we'll see on what databases that they have researched and how the results were there. So first is the graph processing LIGRAPH framework, where they have used the kernel as connected components to the radii and PageRank. Then the data sets that they have used was Enron, which is the email data set. ARXIVGR is the researcher data set, and GNutella is the network data set. And these are the smaller data set that they worked on at first. And then they moved on to the larger data sets, which are the Amazon products and DBLB. These are the graph processing that they worked on. Then they used the in-memory databases. They use the hybrid transaction and analytical processings, where they consider the 64 tables as 64 Excel sheets, and it has 64,000 tuples, where they scaled up them to 640,000 rows. Then they had in the transactional phase, because they both the hybrid transaction and analytical processing. In the transactional phase, they got the 64K updates, and the analytical phase they had 128, 256, and 1024 queries. So the transaction is for the updations, and analyticals is for changing the things that are present in the database. So for developing this, they need to use a kernel. So for selecting the kernel for the NDAs, they have made, highly focused on high memory intensity of the kernel and having a heavy data movement. And among the 3 most consuming functions, it has minimal data overlap with CPU to reduce the coherence traffic. How they implemented in the GEM5. So all these are the simpler terminology of what exactly how they took the things from the normal computer architecture and placed it, but how they actually implemented in the GEM5. For example, for an instance, so we use the malloc for just finding the memory where exactly it is being allocated. But whereas in this simulator, they just placed it as an NDA alloc so that it is specially explaining that it is for the NDA memory allocation. Then for the edge maps, they have used the for the graph, they have used edge map for functions, which is only for the NDA, so that they do not use it on for the CPU, so that that could be easy for them to identify which is for this query is for the NDA and which query is for the CPU. For the IDMBRs, it used analytical queries, which is selector joins on NDA, and other queries, other things on the CPU. So I just mentioned what are the data sets that are being used for the graph. Any one of the data set that is being, yeah, what is the GNitella for? Yeah. So let's continue. Do you think it actually made the things faster? Yes. So I'll just show you the implementation, how exactly. So for an ideal NDA, it shows that there is no coherence. So it will always have a highest peak stage. So when compared, they have used for different data sets, which is the ARXIV, GNitella, Enron, and HTAP. This is for the databases, and this is for the graph databases, and this is for the HTAP is the high transactional analytical processing data sets. So when you compare it with CPU only, NDA only, non-cache, coarse-grained, fine-grained, CoNDA, and ideal NDA, we all know the ideal NDA doesn't have any coherence. So the graph will always be high in every graph. So when compared to all other different mechanisms, the CoNDA is almost nearer to the ideal NDA, which shows it has increased it has made the system more speed when we use the CoNDA protocol. So yeah, so it has made the CPU 66% faster, and it is made 20% faster than the best previous method. The best previous method for speed was fine grained, so it made the CoNDA helped in making it 20% more faster. Within the 10% of ideal NDA performance, CoNDA achieved the near data speed while maintaining the correctness also. So now we just talked about the time. Do you think it also helped in saving the energy? Any take on it? We all know that speed has been increased by just seeing the data sets they have used. Do you think it also saved the energy? Okay. Yeah. Yeah, the answer is absolutely yes. So in the same way, if you see, it is the CPU only NC, coarse-grained, fine-grained, CoNDA, and ideal NDI. So whenever we are increasing the data sets, whenever we are just changing the different types of data sets, always the graph for the ideal NDA, which is represented in yellow, is always the lowest, because the ideal NDA will always have the lowest coherence. So when compared with CoNDA, the CoNDA and the ideal NDA is almost nearer to each other, which shows it also saved the energy. Not only coming to the speed, it also saved the energy for each and every data set that they have worked on. So we can just conclude that it also saves energy. So it has used 43.7% less energy than the CPU only, and 18% lower energy than the next best mechanism, which is coarse-grained. For time, speed, for fine-grained was the best mechanism, but for the memory, it is the coarse-grained. So why did CoNDA save energy? Because it has reduces the communication between the CPUs and NDA, so the energy has been reduced. In the traditional mechanism, it always checks if there is any conflict, and it always reruns the mechanism, which will utilize lots of energy. So whereas in CoNDA, that has been decreased. So the coherent checks were only checked whenever there is a need for it. Okay, so now we have just checked the total mechanism on a one stack. So if we increase the number of stacks, so how will the system perform? Let's look into it. So they have made the workload PageRank on only on the initially only on the ARXIV graph, which is which works on researcher data. They have used the system as a 4 CPU core, and each stack is for local NDA, whereas it stored the NUMA style Macy for the global coherence. The key metrics, yeah. So this shows how exactly the key metrics of off-chip traffic. So this is the first one stack that we have already discussed till now, how it is exactly affecting. So whenever we increase the stacks from 1 to 2 and 2 to 4, even then the CoNDA is always being the best. The CoNDA is always being the best. So for fine grained and coarse grained, there's a sharp rise in the traffic. So whenever from one stack to second stack, this is the fine grained and coarse grained. There is increase in the thing. For the non-cache, it was always high. For the CoNDA, it was very almost minimal when compared with all other different mechanisms that we have compared. Yeah. Why did this CoNDA scale better? Because for when there are more number of stacks, then for the traditional mechanisms, there will be more number of conflicts and there will be more number of caches. So that would decrease the energy and time and increases the time for execution. Decreases the time for execution and increases the energy. For the CPU threads, it was almost 73% of the time for one stack. If it is taking 73 milliseconds, it will take more 70 times or 70 times for the second stack and so on. So for the coarse grain, and it has a heavy invalidation and the performance was lost. Why did the CoNDA win? Because it tracks the read and write sets, and it always have a signature of what is read and what is written, and it always resolves only the real conflicts, which helps in decreasing the decreasing the formulations that need to be done. It keeps the off-chip traffic low and speed up rising with the more stacks. Okay, now let's talk regarding the strengths. The first is the innovative coherence mechanism. The innovative coherence mechanism that they have used is only raise the conflict. If only check the tasks or check all the given things only when there is a conflict that has been occurred. And the comprehensive experimental evaluation, they just did not just did a research verbally and just said it saves energy or it just saves time, but they also did work on the testing on different types of experiment data sets, and they have just found the results. Coming to the strong quantitative improvements, we have already seen it before that we have saved the energy and we made the system more faster, which shows the strong quantitative improvements. The next comes with the low hardware overhead and the program and transparency. So you all never raise a question, like you guys did not raise a question. I'll raise a question. Why did they not do CoNDA run on a real computer? Why did they use a simulator for it? Do you have any idea? Or no, actually because we can just run it on real computer too, so we can just put in on our hardware, we can just add a CoNDA, we can just build it outside and we can just put it on our systems and we can just work on it. But because why didn't we add? Because it is very, very costly, and if you want to check on different caches or different NDAs, then that would be a very difficult task. So that's the reason they have used a simulator, so that they can simulate whatever core CPU that they want, whatever caches they want, whatever operating system they can, so that would make them work more efficiently and get the better result. So for now the GEM5 simulator, they can just directly put it in the backend and they can just work on it. Even the programmer need not always check for the transparency of the GEM5. So this also have made the low hardware overhead and the programmer transparency. And now coming to the weaknesses. So assumptions of the data collisions. Whenever there are multiple data sets that they have been working on, they have seen some collisions which are not valid, but they have seen some rare data collisions, which is one of the weaknesses in the paper. For the lack of real hardware validation. So we have just worked, I just mentioned, we have just worked using a simulator, but it has been very efficient. But we do not know how it will actually perform on a real hardware. So we just need to work even on it. And the Bloom filter false positive. So they have used Bloom filters for just verifying that their conflict is right or wrong. If the Bloom filter says if a Bloom filter gives a false positive, then the total system gets failed. So that is why it is one of the weaknesses, and it has limited workload diversity. They have just did the research on few different types of databases, but they did not work on different on wide variety of databases. So we think that is one of the weaknesses for this. So coming to the things we liked, the novel optimistic coherence mechanism, as we already mentioned, which is the optimistic concurrency control, where it only says to execute the NDA whenever there is unnecessary coherence operations, and it drastically cut down the unnecessary off-chip traffic from the memory correctness. And next is strong empirical evaluation. So they evaluated on the glass processing and a hybrid in-memory databases workloads, providing a broad applicability. And they achieved a 20% performance improvement and 18% energy saving over prior mechanisms, as I've already mentioned you all. Coming to the limited hardware, I've just mentioned we are just using a ZEM5 simulator, but they can just use a FPGA model or a RTL model they can just implement on it, so that would be a great fit. The oversimplified software abstraction. So why is this a weakness? Because they just mentioned in a paper that if NDA begins and NDA end are used in place of begin and end, as in we use for a normal programming. So they just use NDA begin for mentioning it is for an NDA applicable instruction set. So, but when we go for a larger applications, it is not valid to just put an NDA begin and NDA end, so that would not be a consistent one. So that would make more consistency issues and the execution overheads in the application level. So it is a very simple question. He deserves one. Yeah, next question was why. Okay, you can say why. So now coming with our personal experiences reading this paper, before reading this, we never had how the traditional coherence exactly works, but we just got to know how the traditional coherence fails for the near data accelerators by introducing the CoNDA. And we liked how the CoNDA used an optimistic approach for reducing the memory and with the data moment. And it was interesting how they applied for the databases and for the graph applications. And we also never heard about the Bloom filters, which we learned during this paper. And it overall gave a good picture of how hardware and software can work together for a better performance. Before I conclude, I would just ask your reviews on how the paper was and or any other questions that you have for this. Like, what are your takes on paper up until the thing that we have explained, what you understood, or what are the takeaways that we missed that you can mention so that everyone can get it? You'll get a donut. Yeah, okay. Yeah, okay. The Gem5 you're talking about? It is just a chip that is present nearer to the memory, the CPU. Yeah. Yeah. So in this, they have used a Gem5 simulator, which is with 16 cores and 8 wide. So they have 8 instructions per cycle, and it was 16 core CPU that they have used. And
I saw that.
NDAs. Per core 1 NDA. Yeah.
Like, you have to do the calculation, if there is conflict, then you have to re-execute.
Yeah.
Roll back.
Yeah.
So, for example, they are calculating based on their memory.
Okay.
And we are not going to, like, suppose to the system is slow, that so if we want to re-execute, for example, the share based on the share memory, then other cores will need to like wait for that or need to execute. For example, the cascading event.
So basically, I got you. So basically, the NDA only does the read operation, whereas the CPU does both the read and write operation. So if a CPU writes something in the memory, and if the NDA doesn't know that it was written, then that would be a mismatch of the data that wanted to be accessed. So that's when the conflict occurs and the re-execution takes place.
One core or all of the core?
It only takes with the one core where the conflict was occurred.
What about the other cores also, like had some rules?
Yeah.
Have the like old data.
Okay.
They have to re-execute.
They won't get reacted wherever the conflict is occurred. So if we have Shreya has already explained you CPU where there was CPU writes and CPU writes. I can show you. Wait. Just yeah, here. So whenever there is NDA read set and CPU write set not equal to 0, only in that case the commit phase the CoNDA rechecks that the execution will be redone. Until and unless it is 0, the execution will be executed parallelly. All the executions that are executing in the same core will also be executed only if there is NDA read set. So whenever the NDA is reading something and the CPU is, write set has done written something, then that's when the CoNDA gets re-executed. Right. Yes. Sorry. Yeah, they have mentioned. Yeah. Basically, the Gem5 simulator is not actually the real compute system, right? So they just used different types of cores of CPUs, and they just used keeping the NDAs nearer to it. Yeah. 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 Yeah, NDA added to it. So for example, I just put an malloc. Give it. Yeah. actually. Yeah. Or I can continue with the slide if there are no questions. So, in conclusion, it delivers an efficient cache coherence for the near data accelerators for the optimistic execution model. It has a strong balance for the performance, energy, and the correctness, which may close to an ideal coherence models. And it also made it more scalable, efficient, and practical for the real world computing systems. Yeah, I'm up for any questions again. Thank you.
Was a bit long. That's great. So please keep the pace for the next lecture. One more question. Great, ready, great. Hopefully you keep the same rhythm. Please be ready. We have the Thanksgiving holidays coming, so make sure you prepare for them. You really want. But you're right after Thanksgiving. Please give me enough time. A lot of effort. Also, if you like, almost kill. Need a lot of effort. So be ready for that. Just for your benefit, your self-trust. Okay. All right, yeah, great job. See you on Thursday.
అసలు మళ్ళీ గుర్తు చేసుకోవచ్చు
అలా గీత రావచ్చు కదా డోనట్
Oh yeah, everyone, please.